All right, let's go ahead and get started. Hopefully just about everybody is here. So good afternoon, it's good to see you all. My name is Michelle Effros. I'm a professor in electrical engineering. And I thought today I'd tell you a little bit about the area in which I work. I won't tell you about my specific research, but about the area more broadly. And I'd like to tell you about that area by just giving you a little bit of a taste of the kinds of tools that we use. And so, sorry, none of these markers look very good. So let me pull out some of my own. And let me see this. So as I mentioned, my name is Michelle Effros. I'll just write it for you since it may be hard to hear. And I'm a professor in electrical engineering. And in particular, electrical engineering is a really broad field, but my particular field is called information theory. Those of you who may someday want to learn something about information theory, my class on information theory is called EE 126. It's actually cross-listed. I think it's EE/math/CS 126. But in any case, it's an introduction to information theory class. Information theory is a funny field to work in because you all understand something about the word information and something about the word theory, and yet somehow when you put them together, maybe it doesn't mean much to any of you, and hopefully by the end we will know a little bit more about information theory, and eventually, if you're interested, you'll know a lot more. So information theory is one of those unusual fields that started with a single paper. And in that single paper, a single author defined and gave solutions to a really interesting collection of problems to do with communication systems. The single author of that paper was a man named Claude Shannon. How many of you have heard of Claude? Whoa. And the problems that he was interested in had to do with communication. Really basic questions like, is reliable communication in a real or simple model of the real world, is that even possible? Is there any hope that I can transmit information to you in a way that will be reliable? That you can count on your understanding of what I sent being an accurate representation of what I actually said. And we won't really answer those questions today, but if you want to take information theory someday, you'll learn the answers to that question. But I can give you sort of a simple view, a simple introduction to how these questions go, why this is a challenging problem, and the kinds of tools that we use to solve it. So imagine that when you transmit information, you're the communicator now. You're going to send it in the form of binary digits or bits. Bit is just a short form of the word binary digit. So you're going to send either zeros or ones. You'll transmit them as some value that I'll call X. But the person at the other end doesn't necessarily receive the bits that you sent unharmed. So sometimes when you send a zero, what the person at the receiving end, and we'll call what he received Y, what he receives is the same as what you sent. That's what you were hoping for. So when you send a zero, sometimes they get a zero, and when you send a one, sometimes they get a one, but that does not happen all the time. There's some fraction of the time where your bit gets flipped. So you send a zero, but the receiver hears a one, or you send a one, but the receiver hears a zero. And what Shannon imagined is he considered the question, if you just have some model as to how likely each of these events is to occur. For example, in this very simple symmetrical model, you might imagine that the probability that a bit gets flipped is some value p. He asked the question, is there any hope then of communicating reliably? Is there any hope of getting my message across and having the person at the other end correctly interpret it when there's some chance every time you send a bit that bit will get flipped? And the strategy that Shannon took was to think not just about using this channel once, but using it many times, and trying to protect the messages that are transmitted before they're transmitted so that the receiver can reliably understand what it is that you're actually sending. So one way to protect information might be to repeat it. So every time I want to send a 0, I'll send 0, 0, 0. Maybe 3 of them, or 5 of them, or 7 of them, whatever it may be. I'll send multiple repetitions so that lots of things would have to get flipped for you to misinterpret it. So maybe you'll use majority rules at the other end. If there are more zeros than ones, you'll say, I think the transmitter was trying to send me a 0. If there are fewer zeros than ones, that is more ones than zeros, you'll say, oh no, I think they were trying to send a 1, and you'll interpret it that way. And in order to understand how to design the things that you transmit well, notice that you have to understand something about sequences of random events. And I would argue that at its heart, information theory is really about sequences of random events and trying to understand how predictable they are and what does it mean to predict them, what would it mean to do well at a prediction game. And that's what we'll spend today on. So instead of trying to worry about this channel, let's just try and think about a random variable that I'll call z, which I'll say is equal to 1 if the bit is flipped, and 0 if the bit is not flipped. I would argue that if you can get really, really good at understanding what's going to happen with this random variable z, then you'll be really, really good at least that'll be a first step towards this reliable communication problem. So imagine that your task is to just think about z. And really what we're trying to do here is gain some psychic powers, become really good at predicting what's going to happen when you look at long sequences of the z random variable. In this case, because I said z is 1 if the bit is flipped, and we know that the probability of a bit getting flipped is p. We'll say that the probability z equals 1 is p, by which I mean that the proportion of the time that you look at this random variable z, or multiple instances of this random variable z, the proportion of the time that you see a value 1 is p, and the corresponding probability of z equals 0 is 1 minus p, because those are the only values that can be gone, and something has to happen. So if it doesn't come up 1, it must come up 0. If this happens proportion p of the time, this must happen proportion 1 minus p of the time. By the way, how many of you have seen probability at all in any class? Oh, good. All right. So let's imagine now that we have a coin, and we're going to toss that coin many, many times as you're interested in. And each time we toss it, we're looking at an independent and identically distributed instance of this P1 minus P process. I'm sorry, we should be only P. That means that every time I toss the coin, there's some probability P of getting a 1 and some probability 1 minus P of getting a 0, which might correspond to like heads and tails if we think of that. And in order to try and understand how well we can predict these values, in order to solve problems such as this one, although it's not the only example by any means, we're going to try and see what we can do in terms of predicting values we see. All right, so here's how the game we're going to play is going to work. I come to you with this coin. This coin has probability P of heads and 1 minus P of tails. And you all are my potential psychics. I'm in the market for a really good psychic. Each of you gets to tell me how many coin tosses you want to predict, how many times you would like me to flip this coin. And before I flip it, let's say that you choose the number n as your number of times you want me to toss this coin. Before I start flipping, you give me your prediction. Your prediction can be one string of length n, or it can be a list of strings of length n. But we'll count your prediction as correct if what actually happens is in your set, and incorrect if what actually happens is not in your set. So I come to you with this coin. With probability z equals 1 is p. I tell you the value of p. You tell me how many times you want to toss. So how many tosses you want to predict? And then you give me a prediction. I'm going to call your prediction set A sub n. And your set A sub n is some list of things that might happen. Sorry. It's some set of strings, each of length n. You tell me what you think is going to happen, and my goal will be to choose among you the best psychic in the room, the person with the best prediction. Now, I told you that one way we could judge a prediction is the probability with which it's right. So this is the probability that some element in the prediction comes true. We write that probability as the probability of the set A sub n. And the probability of the set A n is just the sum of the probabilities of each element in that set. So it's the probability among all z's in your prediction set that when I do this coin flip, I actually see that particular zn. Is that a good measure of a good prediction?
Best prediction just be one thing considered.
Yeah, if this were our only measure of performance, it's really easy to be a good psychic. Just list everything. You're right all the time. But that doesn't feel satisfying to me as someone paying you for your psychic powers. Because I could have listed everything in advance, right? I didn't need your help for that. So maybe this is one measure that you would want to include, but maybe it's not the only measure. So tell me what else you might care about. What would make a prediction satisfying to you if you were the one paying a psychic for their ability to predict the future?
How many possible sequences are in here?
Yes, we might also care about, sorry, my board use isn't good today, I'm just wandering all over the place, but we might also care about the size of the set of possible predictions. Is that one gonna work for us? Is that gonna be enough? How do I get around this one and still not tell you anything in my prediction? Choose n equals 1. List all strings of length 1. There aren't very many of them, but still not so useful.
Well, I was just gonna say, like, our current number, like this metric that we live by that, to get like an average.
Oh, interesting. So divide this one by that one,
Divide this one that it.
divide this by that. So here's, let's make a list of possibilities. So here's one possibility, here's another one. Divide that one by this one. And just write it as other ideas? What was unsatisfying about listing everything? It wasn't very specific. You know, you go to a psychic and you say, please tell me my future. And they just list every possible thing that can ever happen. If they really could list everything, they'd be right. But you know, specificity kind of matters here. Not really giving you any insight unless they rule a lot of stuff out. The challenge with AN is it depends really a lot on N. Because the space of possible outcomes is big for large N and small for small n, but then still, like, either way, you want to be really specific, right? You want a prediction that actually rules stuff out, not just lists everything, whether that list is long or short. Anyone see a way that we can measure specificity? Only specificity.
How many lists do you have?
How many?
Like lists you have?
How many lists you have. So this was how many elements were in your list. We have only one list as your prediction, so I'm not sure I follow.
I guess I misunderstood things.
Or
You might multiply the ratio in 2 by n.
multiply the ratio in 2 by n.
But more see how more specific the elements of the list will be.
Oh, by n. Yeah,
We want this number to be big.
we want this number to be as big as possible. Maybe. I don't have much intuition about this one. Yes.
I'm not sure how to put this into this, but I was thinking like maybe like normalizing the. You get really closer it is to like make 5 and harder it is to be specific about it, and like whether it is away from that on either the end of 0 or 100. That's how like specific looking at that.
Yeah. Yeah, the idea of normalizing, which is coming up here and maybe here, and in your case as well, I think that normalization idea is a really good one. If you cared only about specificity, maybe a way to normalize would be to look at how big your set is as a fraction of all possible strings that you could have included for your value of n. And say, you know, what fraction did I have to keep to be right this probability, this fraction of the time? Why don't we use those two? So we'll use 2 metrics. And I'll keep them separate so that we can think about them individually. One will be the probability that your prediction is correct. And the other will be the size of your prediction set, the number of strings in your prediction, as a fraction of all possible strings. Now, dealing with two performance measures is challenging. There's some trade-off maybe between them. It's easy to do really, really well. In this case, we want this probability to be as close as possible to 1. We'd like to be right as close as possible to 100% of the time. That's really, really easy to do if you don't worry about this one. Just list everything. Likewise, we'd like this one to be small. We'd like to rule out almost everything, or as much as possible. And that would be easy if you didn't worry about this. List anything. Your set is small, and it may not be right very often, but you know, at least it's small. So if you had just one of these and not the other, doing really well at this game is tricky. But I would argue that doing well with both of them simultaneously may be a little harder. So let's imagine not that we're trying to find the best trade-off between them, but I just set a standard. Look, if you want to be my psychic, you have to be right, I don't know, let's say 90% of the time. And now I ask you all for the predictions A sub n. Well, I first ask you for your value of n and then ask you for your prediction. I will choose the best psychic by figuring out who among the people who met my standard was the most specific. So now I'm going to revise the question to give me a prediction. Or first give me a value n. And a prediction A sub n. Such that the probability of your prediction is greater than or equal to, let's stick with the 90% mark. And your prediction is as specific as possible, which means that the ratio of elements, the fraction of elements that you had to keep to be right 90% of the time is as small as possible. And we will declare the best psychic to be the person who manages to make this value as small as possible without being eliminated for failing to meet my constraint. All right, so let me repeat the game. I come to you with a coin. Its probability of heads, which we're representing by 1, is p. Its probability of tails is 1 minus p. I come to you with this coin, you know the value of p, and I ask you first, how many times do you want me to toss the coin? You give me that value, and we're calling that value n. And then before I do any tossing, you give me your prediction set. It's a list of strings of length n. So maybe if n is 2, you say, I think it's going to be tails, tails, or heads, tails. Those are the 2 items on your list. Each one is a prediction of length 2. And if I do my calculations and find that the probability that the true string is not in this set, I'm sorry, the probability that the true string is in this set is less than 90%, forget it, you're out. You're eliminated from the game. But if in fact, your prediction meets my constraint, it will be right 90% of the time. Now you're in the game, and we calculate your fraction of elements that you had to keep around in order to meet this constraint. Out of all the predictions in the class, each of which can be a different value of n, the person who gets the lowest fraction, the person who is most specific while meeting this constraint that you have to be right 90% of the time, that's our best psychic of the day. That's what you're all signing up. Well, you didn't really sign up for that, but here you are, so you might as well go with it. All right, so tell me, what value of n do you want? Just yell them out. Tell me a value of n. How would you choose n? Someone be brave. I don't even need to know whose voice it was, but give me your N. One. Bunch of ones. Anyone have a choice of one of N not equal to 1? Any other choices in the room? 100. Anyone else? I'm sorry?
67.
67. Awesome. Anyone else?
42.
42. All right. So you all have your values of N in mind. Let's imagine that let me give you a real p-value. Let's imagine that the probability of heads with this coin is 0.2. Just to make something concrete. And now your goal is to come up with a prediction corresponding to your N. If you chose N equals 1, you're giving me a list of strings. Each string is of length 1. So you're telling me, I think it's going to be heads, or oh, I think it's going to be tails, or oh, my set includes both the case where it's heads and the case where it's tails. Whatever set you give me has to have a probability at least 90%. Because that's just what I set as my standard. Everyone understand the game? All right. Let's see how well we can do. It'll be easier to do for N equals 1 than for N equals 100, but let's start somewhere. We'll start with the easiest case and then try and reason about what the best prediction looks like and how well that best prediction can be, how well that best prediction can look. So let's imagine that N equals 1 just as the easiest case. With N equals 1, remember that there are only 2 possible outcomes, which I'll represent with this little tree. The outcome can be a 1 with probability 0.2 or a 0 with probability 0.8. That is 20% of the time when I flip this coin, I get heads, which we're representing by 1, and the other 80% I get tails. Now, if you wanted to make the best possible prediction, I'll call it A1 star, as the best possible prediction, the most specific prediction you can come up with, that is right at least 90% of the time. What does A1 star have to look like? Yes. It has to list both of them. How did you get there? Well, you put in the most probable element, the 1. You're only right 80% of the time. So that's not enough. And so you put in the next most probable element. That's the 0. Now you're right 100% of the time. That was the smallest set that you could come up with that was right at least 90% of the time. Notice in our problem definition, there's no extra credit for being right more than 90%, like a lot more than 90% of the time. You just had to be above the bar. So this prediction meets the constraint. The probability of this set is equal to 1, which is, of course, greater than or equal to the 90% that was required of us. And how specific is this set? What is the fraction of elements that we had to keep around? It's 1, right? So we were right 90% of the time, but we weren't very specific. We didn't actually rule anything out. Let's try N equals 2. Now we have 4 possible outcomes. Every time I branch left, I'm making a 0. I'm calling that the tails. This is tails in the first flip, tails in the second flip, and so on. And what is the probability when you have a coin that 80% of the time gives you tails? What's the probability that you see tails followed by tails? 0.64. It's 0.8, the probability of getting the first tail, times another 0.8, the probability of getting a tails on the second time. So 64%. To get the probability of a 0, 1, you do 0.8 times 0.2, which gives you 0.16. 0.2 times 0.8 gives you 0.16, and 0.2 times 0.2 gives you 0.04. All right, let's try and design the best possible prediction for strings of length 2. What are you going to put in there first? Put the 0, 0 string in because it has the most probability. This was 0.64. 0.64 doesn't get us over our 90% mark. So we'll add in the next most probable, and there's a tie here. Doesn't matter which one you add in next. I'll just keep working my way from left to right. So I'll put in this next prediction, 0, 1. It has probability 0.16. Does that get us to the 90% mark? No. So we keep going, right? We add one more element in. Always a good idea to add the most probable thing. It'll get you over that bar as quickly as possible. So you add this one in, and now you're at what? 0.96, which is above our 90% bar. So we have the probability of this prediction is equal to 0.96, which is greater than or equal to our 0.90. So we've qualified to compete. And now we look at what fraction of elements we had to keep around in order to get us over that bar. And we kept around 3. There were 4 possible outcomes altogether. So we kept around 3/4. Which psychic would you rather have, that n equals 1 psychic or that n equals 2 psychic? N equals 2. You were right 90% of the time, and you only had to list 75% of all possible strings. Looks a little better. Let's try n equals 3. I'm just working my way up. Now we have a tree with 8. Maybe I should start at the bottom of the tree to make sure everything fits. Now we have a tree with 8 leaves, representing all strings of length 3. This is 0, 0, 0, 0, 0, 1, and so on. Every left branch is a 0, every right branch is a 1. I'm not going to label all of them. What's the probability of seeing a 0 followed by a 0 followed by a 0? 0.2 times 0.2 times 0.2. 0.2, 0.2, 0.2. Did I get that right?
Yeah, isn't 0.8?
I'm sorry?
Isn't the probability of getting 0.8?
Oh, I'm sorry. I got it backwards. Yes, sorry. 0.8 times 0.8 times 0.8. I'm sorry, what is it?
I went to
512. Thank you. Now we have 0.8 times 0.8 times 0.2, which is 0.128. That was for 0, 0, 1. 0, 1, 0 is also 0.8 times 0.8 times 0.2. So it's going to give you the same number. And 1, 0, 0 is also going to give you 0.8 times 0.8 times 0.2. So this one is also going to be 0.128. Multiplying those numbers together in a different order isn't going to change what they evaluate to. So you just need to know the number of lefts and rights in this tree. How about 0.8 times 0.8? I'm sorry, 0.8 times 0.2 times 0.2. 0.032, thank you. And that one likewise is going to occur in both of these cases. It's equal to 0.8 times 0.2 times 0.2. And again, it doesn't matter in which order you saw your 2 ones versus your 1 zeros. That's why it's showing up in 3 places. And in this case, we get 0.2 times 0.2 times 0.2, which is that 0.008 value that I mistakenly wrote earlier. Did I fill this in correctly? Catch me if I have any mistakes. Doing math on the fly, always dangerous on the board, especially. All right, assuming that we got that right, let's come up with our best possible prediction. I'll just write it a little bit lower since I didn't leave myself very much room. Now we're coming up with a collection of predictions, each of length 3. We're going to put the most probable one in first. And the most probable one in this example is 0, 0, 0. That gave us a probability of 0.512. Did that get us over the 90% mark? No, so we keep going. We take the next most probable element, and there are ties here. It doesn't matter which ones you take, but I'll work my way left to right. So 0, 0, 1 will be my next addition to this set. That one had probability 0.128. Does 0.512 plus 0.128 get me over the 90% mark? No, it doesn't. So let's add another one. This is also 0.128. Does that get us over the 90% mark? Nope, still not. We'll keep going. The next one of that highest probability is this one, which is 1, 0, 0. Are we over the bar now? Nope, still not. We need one more, so let's take one of these 0, 1, 1. Are we over the 90% mark? We are. Hallelujah. So now we're in the game. We won't keep adding elements because we're trying to be as specific as possible. We get a probability greater than 90%, so we're in. And what is our specificity? We had 8 possible strings in this tree of depth 3, this binary tree of depth 3, and we used 1, 2, 3, 4, 5 of them. So our specificity is 5/8. All right, which is better? A 1 star, a 2 star, or a 3 star? What's the best of all of our predictions so far? A 3 star. Anyone see a trend? They're getting better and better every time, right? Is that always going to be true, or was that luck? Why? I don't know who said it, but why do you believe it should always be true?
Because, I mean, if you have any like specificity of 2, or like any n, you can consider the same elements that you had and add a 0 and 1 to the end of each string. And consider that set of elements. That's always gonna be over 90% to begin with. And that's gonna be at the same specificity. But you can maybe remove the least element, and that could get only better.
So an argument was just made. Here's the claim that was made. Given the best prediction, I'll say instead of the best prediction, a best prediction. For sequences of length, for n tosses, let's say. I say A rather than B because it's not unique. You saw with these ties, I could have made different choices. They would have been equally good. The claim is that the specificity AN plus 1 star is less than or equal to the specificity of n. Notice that you claimed actually strictly better. I'm going to make that a little bit gentler and say no worse. But not strictly better, which is why I have a less than or equal to instead of a strictly less than. So far it's been strictly less than, but I won't make that claim that it will always be strictly less than, but I will use your argument, because I think that's what your argument shows, to suggest that it will be no worse than what you got. Oh, I'm sorry, this should have been. So the specificity of the best prediction of length n plus 1 is better than, or no worse than actually, the specificity of the best prediction. And the proof that was offered was the following. Given a n star, we will design a new prediction. I'll call it an plus 1 without the star because the claim was not that it's the best prediction, it's just a prediction. And the way I'm going to design it is to take the set an and follow it with every element in this set with a 0, that's one element in an plus 1, and every element of this set followed by a 1 is another element. In other words, this is the set of all strings of length n plus 1. For which xn is in the set an, and xn plus 1 is anything. Notice that the probability of this set, which is just the sum over all strings in this set, of the probability of those strings, can be broken down into the sum over all strings in our prior prediction set. Oh, this should have had a star on it. In our prior prediction set, followed by a 0, plus the probability of all strings in our prior prediction set followed by a 1. I guess that's just how we define the set. And if you add up the probability of each string followed by a 0 and the probability of each string followed by a 1, because this is all possible outcomes, this is just the probability of the xn itself. Those of you who haven't had probability yet can hopefully at least understand the intuition that if you list everything that can happen afterwards, the probability of the event that you get, including all possible things that follow, is just the probability of seeing whatever xn you were looking at in your first n tosses. And so this thing is equal to the probability of an star, which was greater than or equal to our 90%, because that was the definition of an star. It was the best prediction, meeting the constraints of our game. And so this one meets the constraints as well. And how well did this do in specificity? The specificity of our prediction, sorry, this is an plus 1. The specificity of our prediction was, well, this set was twice as big as the set an star, because we followed all possible strings in an star by a 0 and by a 1, 2 different predictions. So we get something twice as large. But this one is also twice as large. And so together we get, this is equal to the specificity of our best prediction of length n. Which means that the best prediction of length n plus 1, which certainly has a specificity that's at least as good as this prediction of length n plus 1, must have a specificity that's no worse than the specificity that you could get at length n. Which proves the claim. Yeah? Now, notice what we have here. The best prediction with n coin tosses is no worse than the best prediction with n coin tosses for every n. So, if you want to predict the future, go long. Don't try and predict what's going to happen in the stock market tomorrow. Try and predict what's going to happen over lots of uses of this game. Now, the stock market is not IIT like our coin toss is, so, you know, caveats may apply, but the suggestion is reasonable. Think long run, don't think short term when you're trying to predict the future, if being specific matters. Question?
Can you write the best prediction for momentum?
I'm sorry, can we, oh, if you have a model, you could play this game for your model of probabilities, no matter what your model of probabilities is. But we are absolutely relying on knowing something about the statistics in designing our prediction. The mechanism that we use to design the best prediction will always be the same. You'll put in your most probable element and then your next most probable, or your most probable string and your next most probable and so on, but which string that is will vary depending upon the model. So if you have memory and it's not independent, your predictions will change to take that memory into account. But you can definitely play the game.
What's that? N plus one is less than or equal to, like, AMX star, so that implies a point where it's not, where even if you keep adding, then you're not gonna get any better result. And so my question is, how do you find that if it exists?
So that's where we're going. Thank you for your question. I did not plant the question in the audience, I promise. So notice what we have here. We have that the best possible prediction for one coin toss is no better in specificity than the best possible prediction with two coin tosses. Oops, and so on. So this is greater than or equal to A3, and so on, ad infinitum. Which means that this sequence of specificities, let me call this S1 and S2 and so on, is non-increasing. It's also bounded below by 0. You certainly can't be more specific than to rule out everything. So S sub n is non-increasing and bounded below. And what do we know about sequences that are non-increasing and bounded below? They converge. They converge. Thank you. Very nice. And the question you should be wondering about is, what do they do? So you want to be right 90% of the time. You want to be as specific as possible. And if you knew what this sequence converges to, you would know how specific you can be. That is, what fraction of elements do you have to keep around in order to be right 90% of the time for this particular coin that has probability 0.8 of tails and 0.2 of heads. Unfortunately, we don't have time to do this calculation, but it's one of the first things that we do in information theory class. But you tell me some guesses. What do you think it converges to? You want to be right 90% of the time. What fraction of elements do you have to keep around? Yes. No, I'm guessing. 1/2. You want to be right 90% of the time. You have to keep around half of the elements. So far, we had made it down to 5/8. We were a little bit bigger than a half. Maybe we're converging to a half. That's pretty impressive, right? We can be right 90% of the time and keep around only half the elements. Any other guesses?
One over E.
1 over E. Why 1 over E?
Simply because E is always up here.
This E shows up everywhere. Awesome. This value, E is a little bigger than 2. A little smaller than that one. Still, you're right 90% of the time and you have fewer than half of the elements in your prediction. Other guesses? Does it converge? Let's find out. It converges to 0. Exactly. You can be awesome settings. this value converges to 0. The fraction of elements that you have to keep around in your prediction set to be right 90% of the time converges to 0. So you can be right 90% of the time and keep around a fraction as close to 0 as you'd like. Notice this does not imply that the size of your prediction set is shrinking. It only implies that the fraction is shrinking. But still, you can be right 90% of the time for this coin and keep around a fraction as close to 0 as you want by making a margin. Question?
Random observation, but is it a coincidence that the numerator is Fibonacci sequence numbers?
Yes, I think it is.
Because I thought maybe like you could always refer to what term it is and then divide it by 2 until like the nth term of that sequence table. And that way I can prove it goes to 0. But other than that, you just have to do every single number of.
You don't. You don't have to do every number. There is a systematic way to prove that this ratio goes to 0. We will not do that in the 5 minutes left of class, but let me tell you a little bit more about this result. Did this result depend on the value 0.2, 0.8 for our coin? A little bit. It works no matter what your coin is, unless your coin is half-half. If your coin is half-half, if it's a perfectly fair coin, if life were perfectly fair events are not predictable. Why? Because every single string is equally probable, and if you want to be right 90% of the time, you got to have 90% of them. There's no way around that, because they're all equally probable. We're taking advantage of the fact that some are more probable than others, for sure, in getting this result. Did the 90% matter? Nope. As long as you choose a standard that is strictly less than 1, because to be right 100% of the time, you just need everything that can actually occur. So as long as your standard is strictly less than 1, the same result applies. You can be right 99.99999% of the time, while ruling out 99.9999% of all outcomes. The fraction of elements that you have to keep around goes to 0. So you can be extremely specific while being extremely accurate, being right most of the time, as long as life is not fair. That is, you're not trying to predict equally likely outcomes, and you're not forcing yourself to be right 100%. As long as you're at that just below the bar, but as close as you want to be, you can be awesome sidekicks, which will not only help you in a class like information theory, but I would argue will help you in all kinds of different aspects of life. So I'll go ahead and stop there. I'm happy to answer any questions. Thank you all. I appreciate your participation, and it was nice to see you all.
Anything starting with 0 would be 0.8. So everything at this point is funny. So if you have these alpha sets containing